For our fifth example, we have a problem from chapter 14 in the textbook that deals with the equilibrium constant. And the problem states that at the start of a reaction, there are 0.249 moles of N2, 3.21 times 10 to the negative 2 moles of H2, and 6.42 times 10 to the negative 4 moles of NH3 in a 3.5 liter reaction vessel at 375 degrees Celsius. If the equilibrium constant for the reaction is 1.2 at this temperature, is the system at equilibrium? And if not, predict which way the net reaction will proceed. And here we have our net reaction, and all we need to solve this problem is the reaction quotient equation. And our reaction quotient equation is actually identical to the equilibrium constant equation, which has products divided by reactants. Now, we need to know that even though the K and Q equations are the same, their values mean different things when it comes to the direction of a reaction, but we'll get more into that towards the end of the problem. So to begin, we first need to find our initial concentrations of our compounds. So let's start with N2. N2 is equal to, has 0.249 moles, and this is going to be divided by our liters. And we're going to go ahead and do this, follow the same process for all of our compounds. H2 is equal to 3.21 times 10 to the negative 2 moles. Also over 3.5 liters. And then we have NH3 equal to 6.42 times 10 to the negative 4 moles over 3.50 liters. Alright, and now I'm going to plug each of these into the calculators. And for N2, we have 0.0711 molarity. For H2, we have 9.17 times 10 to the negative 3 molarity. And for NH3, we have 1.83 times 10 to the negative 4 molarity. So, now that we have found our molarity, or the concentrations of each of our compounds, we can go ahead and plug it into our reaction quotient equation, which I've already written up here in terms of our reaction. So we have QC, we have the product on top, NH3, which we found the concentration to be 183 times 10 to the negative 4 molarity. And on the bottom, we have our reactants, N2 at 0.0711 molarity, multiplied times the molarity of H2, which is 9.17 times 10 to the negative 3. And when we plug this into the calculator, we get 0.611. And this is the reaction quotient constant of this reaction. However, we're not done yet. So we're given that the equilibrium constant is equal to 1.2. And we have just found that our reaction quotient is equal to 0.61. And you can tell just by looking at them that they're not equal, so this reaction is not at equilibrium, but Q is less than K. So when Q is less than K, that means that the ratio of initial concentrations of products to reactants is too low. So to reach equilibrium, more reactants must create more products. This means that the reaction must move from left to right.